So let's now look at what would happen if I have more complicated circuits with more than one resistive element and more than one capacitive element. So we went over this in class on Friday, but let me remind you of how this works. So I have a battery. Kirchhoff's rules tell me that the total change in voltage across a closed circuit has to be 0. So if I have a battery voltage E, if you like, I can write Kirchhoff's rules as E minus V1 minus V2 minus V3 is equal to 0, which gives me E is equal to V1 plus V2 plus V3. So that's the first application of Kirchhoff's rules to this circuit. Now, when I have combinations of resistors, the point is to simplify the system. Okay? Can I, rather than thinking of each individually, combine them and think of just one resistor? This is not always possible. So it's not always possible to replace a whole bunch of resistors by a single resistor. But maybe it's possible in small segments. So at least in this case, where the same current is flowing through all three resistors, it's possible to take these three and replace them by one. So finding the equivalent resistance of a combination means taking that bunch of resistors you have and replacing them by one. Okay? The effect of the one should be the same as the effect of the three. So the power dissipated in this equivalent resistance should be the power dissipated in the combination of all three. That is to say, if I add the power here and here and here, I should get the power dissipated in the equivalent resistance. The battery is the same. So once again, when I'm replacing it by equivalent resistance, the current that's flowing through the battery in this case should be the same as the current that's flowing through the battery in this case. And that is what gives you the clue for how to solve this, because you say if the current is the same, then let me write this in terms of the so this loop rule circuit, the loop rule for this circuit is just E minus R equivalent times I is equal to 0. E minus I R1 minus I R2 minus I R3 is equal to 0. Why can I put the same I here and here? Because it's the same I going through the battery. Okay, so if I now equate E on both sides, E is equal to R equivalent times I, E is equal to I times R1 plus R2 plus R3, then you just see that R equivalent is R1 plus R2 plus R3. So what you're saying is R equivalent times I is equal to R1 plus R2 plus R3 times I. Okay? So in a series circuit, this is a series combination, you have the same current flowing through all of them. Okay, let's do the resistors in parallel first and then come back and think about each of those circuits separately. In the case of resistors in parallel, okay, what does it mean to be in parallel? That means each pair of resistors that are in parallel, why are R1 and R2 in parallel? Remember, there's no voltage drop across connecting wires. So let me compare this point with this point. Okay? And let me do it in a different color. This with this. The two blue points are connected to the positive terminal of the battery. So everywhere on this side of the three resistors, and I should add the third thing, all these blue points are at the same voltage as the positive terminal of the battery. All the green points are at the same voltage as the negative terminal of the battery, because these are connecting wires. There's no voltage drop across them. So the change in voltage across each resistor is the same. Right? So V across resistor 1, V across resistor 2, and V across resistor 3 are all equal. So what is the same over here is V1 is equal to V2 is equal to V3. Actually, let me go back for a second to the series circuit and tell you what is the same over here is that, let's do it in a different color, I1 is equal to I2 is equal to I3. So in the series combination, the current is the same. In the parallel combination, the voltage V1 is equal to V2 is equal to V3. Okay, but what about the currents? So for the current, you want to use the junction rule. So this current conservation, which is the junction rule, is telling you that if I take the current going through the battery, okay, that reaches this point and divides into two. So it divides into I1 and then it divides into whatever goes into this portion of the circuit. Then when it reaches this next blue point, it divides further. Some of it goes through R2, some of it goes through R3. So if I look at everything coming into I1, into point A, which is the first blue point over here, there's the total current entering, that's I. The total current leaving is I1 plus whatever goes here. Now whatever goes here further divides into I2 and I3. So I can say then I entering this point is equal to the total current going through each of the resistors. But those currents are not equal necessarily. Under what circumstances would those currents be the same? The voltage is the same across each resistor. If the resistance is the same, exactly. Only if the resistors are the same will they have equal currents going through them. Okay? But otherwise, in general, the currents are different, but they do add up to give you the total current. Now, once again, you're taking this combination and you're replacing it by an equivalent resistance. So you're taking these three resistors and replacing them by one. The total current going through the battery in this case too is the same as the current that was going through the battery here. So if I want to now use Ohm's law, once again, you're using Ohm's law just like in the previous case with series resistors. And you're saying Ohm's law tells me V1 is equal to I1 R1. V2 is equal to I2 R2. V3 is equal to I3 R3. And in the equivalent case, E is equal to R equivalent times I. So I take each of these and I write these in terms of the currents I. So I is equal to E over R equivalent. And that goes on to into the left-hand side. Then I do the same over here. I write I1 is equal to V1 over R1. And likewise. So then what you realize is that V1 and V2 and V3 are all equal to E. So E is equal to, what I'm going to get from this equation over here is E over R equivalent, which is I1, is equal to I1 plus I2 plus I3. E over R equivalent is equal to E over R1 plus E over R2 plus E over R3. And once again, E1, E will cancel everywhere. You can divide through by E, and I get 1 over R equivalent is equal to 1 over R1 plus 1 over R2 plus 1 over R. So what you're equating now, what is the same in the case of the parallel combination is the voltage. What is not the same is the currents add. What is the same in the case of the series combination is the current, the voltages add. Okay, so this summarizes these two combinations.